When Roald Dahl wrote about Willy Wonka's magical space elevator in 1972's Charlie and the Great Glass Elevator, the scientific community didn't really think, oh wow, that's a serious business that we could definitely make. And honestly, why would they? It was the sequel to a book about a raving lunatic who built a candy factory that defied science and was run essentially by slave labor. Oompa loompa. However, Arthur C. Clarke's The Fountains of Paradise from 1979 received a lot more attention, what with the focus being on, actual science rather than magic and, well, bullshit. While Clarke's book brought the idea into the mainstream, it was hardly the origin of this invention. The idea of a space elevator was actually first published all the way back in 1895 by Russian scientist Konstantin Tsiolkovsky, a little over a decade after the first electric elevator was invented. Even then, one could argue that the space elevator is more of a high-tech version of the Tower of Babel from the Bible's book of Genesis, making the concept thousands of years old. And again, scientists did look at the Bible and were like, ooh, that Tower of Babel. Chop to it, let's make that! In a way, it makes a lot of sense that the idea would have such low-tech origins. Humans are pretty good at building exceptionally tall structures, so why then shouldn't we be able to build something as tall as we want? Oh, I don't know. The limits of engineering, architecture, and science, maybe? And now look, the tallest building in the world, the Burj Khalifa, is still less than a kilometer tall. The Kármán line, the boundary between Earth's atmosphere and outer space, is 100 kilometers above sea level, and low Earth orbit is about 2,000 kilometers up. So we've got a ways to go. And look, not only are these orders of magnitude bigger than anything we've ever built before, neither of those numbers are even close to how tall a space elevator would need to be. Now look, at first glance it may just seem like a bit of a pipe dream, but companies in China and Japan believe they could have one built by 2050 at the latest. That seems wildly optimistic, my dudes. And if they're wrong, this would make it the first time in history that a company has ever lied about the viability of a project in order to acquire money from investors. That never happens. Theranos. Allegedly. What exactly is a space elevator? The space elevator is exactly what it sounds like. It's an elevator that takes you to space! But it's not designed in the way that you might think. The elevator would be a cable that connects the Earth and extends out into space. And attached to this cable would be a climber, which serves a similar purpose as a car in a more traditional elevator. So far, so good. Now this climber then carries its payload up the cable and into space. The climber sounds like it was taken from some science fiction book. Why not just call it a car? Why not just call it the box in the lift thing? Easy. It seems simple enough, and it would be a huge deal if we could actually build one of these. The ability to get supplies and other cargo into space without needing to burn rocket fuel would be absolutely massive. To many, the construction of a space elevator is the point at which humans could truly say that we had become a spacefaring society. However, it is more complicated than just building a really tall elevator. Earth has gravity. It's a shocking realization, I know. And that gravity causes compression of large structures. Now we can account for this by building wider bases for these structures and having them taper as they get higher, which of course provides more stability. But it's not going to surprise you to learn that this has its limits, and building a compression tower into deep space isn't even remotely possible. There simply is no material with the compressive strength to hold up its own weight under the conditions that would be required. Now, fortunately, in 1959, Russian engineer Yuri Artsetanov realized that we don't need to build up from Earth into space. We can launch the elevator into space, then have it deploy the cable back down to Earth, where it will be anchored somewhere on the equator. Big brain. Now, the first step would be to launch something into geosynchronous orbit, meaning that it orbits the Earth at the exact same speed that the Earth is rotating. Now, this is important because we need the elevator to go up in a straight line. It's also why the elevator needs to be tethered at the equator. The planet rotates faster at the equator since that's the widest point. If the elevator is tethered in Washington or Moscow, the satellite in geosynchronous orbit would be orbiting at a faster rate than the part of the Earth that was rotating, and the cable would start to wrap around the planet rather than extending outwards in a straight line. And that's going to be a bad time. Now that we know where we need the satellite positioned and where we need it tethered, there's the oh-so-small matter of just lowering a cable down to Earth from a satellite really far away. Now look, we can't just lower the cable by itself because doing so would change the center of mass of the orbiting object. As the center of mass got closer to the Earth, it would change the trajectory of the satellite and pull it out of its geosynchronous state, which would be bad news for the project. It's good we thought about this ahead of time. Then luckily, there is a very easy fix. Look, instead of just deploying a cable down from the satellite, we'd need to also extend a cable up in the opposite direction with a counterweight attached at the same time that the cable was being lowered to Earth. Again, this is some real big brain stuff here. This is not only necessary to maintain a stable orbit, but it produces a very interesting effect. Everything below the line of geostationary orbit will be pulling down towards Earth thanks to the force of gravity. However, everything above the line is going to be pulling up thanks to the centrifugal force produced by the rotation of the counterweight, which is extremely cool. Now, this results in a cable that is otherwise just floating in space becoming taut, and it's known as a tensile structure. Now, if you've watched Stranger Things, you'd have seen the same effect when a rope is tossed between the real world and the upside down. As a tensile structure, the cable would not have any compression or bending, which is perfect for our purposes. Now, once that cable is fully lowered to Earth, it would then be attached to a base at the equator. Now, originally, the base was intended to be some sort of stationary structure, though more recent plans have been for the base to be on a maneuverable ship in the ocean for, well, reasons that we're going to address in just a moment. Now, the premise of a space elevator does seem pretty simple, and honestly, the execution doesn't seem that hard. It's a bold statement, Kevin, who wrote this. When it was originally conceived as a compression structure that was built upwards, it would be just utterly impossible. But as a tensile structure that is built down, it seems a lot more feasible. We have no problem launching shit into space all the time, and we understand what needs to be done. So, what exactly is stopping us? Well, a lot of stuff that we are about to get into. The hurdles. The math for building a space elevator is pretty straightforward. That's not to say that it isn't complicated, but there's not a lot of variables. Things like the mass of the Earth and the universal gravitational constant are, well, constant. And if those things became non-constant, then there'd be a lot more to worry about than this fancy elevator that we're building. In fact, there's only one variable that we have any control over, which is the density of the cable. Because the calculations are straightforward, we can easily determine the maximum tensile stress of the cable. And it's going to be big, guys. It's going to be real big. That's where the problems begin. If we were to build the cable out of steel, for example, the stress the cable would be under is over 200 times the tensile strength of steel. This would mean that it fails in spectacular fashion, so steel is not going to cut it. Or at least it isn't going to work if the cable is uniform in width. A proposed solution is a tapered tower. The further we get from the satellite at geosynchronous orbit, the less tensile strength there is. Think of it like a game of tug of war. The stress on the rope is all at the center. If the rope was going to suddenly snap, there's no danger of it happening near one of the ends. There's virtually no stress on the ends of the cable. By tapering the tower at both ends and reinforcing it as it gets closer to the center, the problem could be solved, at least kind of. If we still wanted to use steel, the maths shows that there is a ratio by which it could be tapered without the elevator cable snapping. A hilarious, utterly impossible ratio, that is. All we need to do is have the cable be microscopically thin as it anchors to the Earth and expand as it approaches the satellite until it's trillions of trillions of trillions times wider than the entire known universe. Bad news for our steel cable. Look, there are less dense materials than steel, but they still leave a lot to be desired. Kevlar and carbon fiber are both dramatically better for building this cable, but they would still need to reach a diameter of 80 to 170 meters wide. Now, at least those numbers would fit well inside our universe, but they're still just not feasible. So that just leaves one option, the material that scientists believe will make space elevators possible: carbon nanotubes. Multi-walled carbon nanotubes have only about a quarter of the density of steel, but they have as much as 100 times the tensile strength. They have the exact properties that we need to make a space elevator a reality, but that doesn't mean there isn't still a problem. Carbon nanotubes are small. They are typically only a couple of centimeters long, with the record being about half a meter. Our goal is to make a cable of carbon nanotubes that reaches geosynchronous orbit. which is roughly 36,000 kilometers from the equator. It's a lot more than half a meter. And don't forget, this cable needs to extend in both directions from orbit. Our ability to mass produce carbon nanotubes needs to be dramatically increased in order for this to be at all remotely possible. Actually, almost certainly increased with time. That just leaves a couple of other problems. One is powering the climber. There are a few proposals for how this will be done. The first is solar power. After climbing the first 40 kilometers, it should be possible to power the climber entirely through solar power. For the first 40 kilometers, some sort of wireless energy transfer is proposed, such as using laser power beams aimed at the bottom of the climber, which is cool. I always prefer a science fiction where there are lasers. Another popular option is nuclear energy, essentially storing all of the required energy for the climb in a nuclear battery. There have also been proposals of using a second cable that provides power to the first by utilizing the incredible conductivity of carbon nanotubes. That's hard to say which will be the most practical option, but scientists are actually already testing this shit, which is cool. Many different organizations around the world are conducting tests and competitions to build and power climbers that could be used for space elevators. These are obviously small-scale tests compared to what the real thing will look like, but right now, we're just looking for a proof of concept before trying to scale it up dramatically into space. But once we do scale it up, there's one final problem that space elevators are going to need to handle, and that's the fact there's a lot of shit in space. There are tens of thousands of space debris in low Earth orbit, and the last thing we'd want is for them to collide with the cable. This is why current proposals have the cable tethered to a mobile base on a ship rather than something stationary on land. This would provide the cable with some amount of maneuverability to avoid this debris as long as we can see it coming. Now, in the event that the cable does break, there are conflicting reports of how bad it would be. Anything above where the cable breaks should be pulled by the counterweight and fly off into space. Everything below it would fall back to Earth, and this has been depicted both as a global catastrophe and as something completely harmless like a ribbon just falling to the ground. The reality is likely somewhere in between, in that it would suck and probably cause some damage if it didn't all land in the water, but it would hardly be the end of life on Earth as we know it. Wrap up. So, could we really build an elevator into space? Almost certainly. Yes, good news. Nothing about the idea violates the laws of physics, and from a purely mathematical standpoint, it should be possible with improvements in the production of carbon nanotubes. Unlike pointless novelties like hoverboards and lightsabers, this is something that is seen as a genuine scientific pursuit. That means there is a lot of active research and development going on, and it's almost certainly a matter of when, not if. Companies we mentioned earlier both have estimates that an elevator will be completed by 2050, if not earlier, but don't get too excited about that just yet. A space elevator will be a revolutionary invention and a turning point in the course of human civilization. The importance of such an invention cannot be overstated. However, don't for a moment think that in 30 years you'll be able to just hop on an elevator and visit the ISS as a tourist. The ISS won't be there, and well, neither will your space elevator. Estimates for how long it would take a climber to go from Earth to the top of the cable range from 2 to 8 days. At least in the beginning, this is just going to be a freight elevator, not really intended for transporting people. It would probably be impossible, or at the very least, extremely unsafe for a person to use the first iteration of a space elevator. Even if it is possible, it would be an incredibly shitty and boring ride. Once the technology improves and space elevators can be used to transport people, just hope you aren't the person riding one when unexpected space debris cuts the cable and sends you hurtling off into the depths of space. It's terrifying. Thanks for watching.